All right, let's do a quick overview of galaxy types. The book has a good summary of all this, but it's just good to hit the highlights. Remember that we are in a spiral, right? And we said last time that spirals have all of them have the same kind of characteristics. The spiral arms are blue because of the active star formation there, along with a really active little pink spots where stars are actively being born. The nucleus of the galaxy generally is sort of yellowish because not so much active star formation is going on. And then there's a halo, older stars, globular clusters. Okay, I don't know. Spirals are maybe something like 40% of all galaxies. Current galaxies tend to be spirals, something. Another 40% or so are ellipticals. And elliptical galaxies are really sort of gigantic globular clusters. The striking difference between they and spirals, apart from the fact that they don't look like spirals, right? They're basically spherical. The degree to which some of them can get sort of flattened out. But anyway, most of them are spherical or football shaped. But here's the big deal, is that for some reason, as opposed to spirals, they have little to no star formation and no gas and dust. And so they tend to be sort of yellowish or reddish colored because they have an older population of stars in them. What I'm not going to do is sort of tell you why. Spoiler alert, kind of a cliffhanger. Anyway, to read the next chapter. But there are reasons for that we'll talk about next week as we start winding things up. Why is it that so many galaxies are either star forming or not star, have a totally different shape? Well, there's a reason, I think, and we'll talk about it. Yep. And then there's sort of a catch-all category of small galaxies called irregulars. Now, if they're small and we see them, that must mean that they're pretty bright, because they usually have bursts of star formation going on, so they tend to be bluish in color, and they tend to be small. But these are the three major types. Galaxies gather together in groups, clusters. Here's our local cluster. There's us, Milky Way galaxy, and notice, look, we're surrounded by a number of small satellite galaxies, sort of like, a giant planet, its moons. So big galaxies tend to be surrounded by smaller galaxies, usually dwarf irregulars, and these just sort of orbit the main galaxy. So in our group, called the local group, in our galaxy cluster, there are about 30 to 40 galaxies, but there's only two major galaxies cluster. Thus, Andromeda. Andromeda is a bigger spiral than us. We're not the biggest one. Andromeda is maybe twice as big, something like that. But notice that it also has a little fleet of galaxies around it. And the way that it works is often galaxies inside of a cluster are all sort of wandering around, and they're gravitationally bound to each other, sort of in orbit around the center. It just so happens that our galaxy and Andromeda's are coming at each other. And so in about something like 3 to 4 billion years, our galaxies are going to collide. Collide is probably overstating it. It's sort of like when two clouds run into each other. There's not an explosion or anything, but the structure of the galaxies is going to be kind of messed up. The stars, remember, are so widely separated that it's not like anything, like the stars aren't going to blow up. They just sort of, right? But the structure of the galaxies change. How it's going to change. Okay, so that's our local group. There's Andromeda. We think our galaxy looks something like this, but you can kind of tell here Andromeda is seen a little bit more edge on, so it's a little tough to pick out the spiral arms, but you can pretty clearly see the lanes of gas and dust. And then here's one of its satellite galaxies around it. And then here is another cluster that's farther away. And look, if you can, go look up pictures of the Hercules cluster. It's pretty cool. And I think this is actually a link. I think if you click on this in the PDF, it'll take you to a big image of the Hercules cluster. But look, in this cluster, there are hundreds of galaxies, and a lot of them are large. And look how they're interacting. Look at this pair. Look at this pair down here. There's two spirals that are interacting together. Here's one. Here's a spiral. And thick. Anyway, here is a spiral interacting with another galaxy, and what tends to happen is that their disks become warped, kind of S-shaped. So that's a neat couple that's interacting together. Look at these two over here. These two are kind of spiraling around each other and throwing off great clouds of stars, gas, and dust. Anyway, lots of good examples of interacting galaxies here in the Hercules cluster. Ooh, here's another one. Look at that. Kind of pretty. There's a face-on spiral and then an edge-on spiral, and look how the shape of the disk is getting kind of warped by their interaction. So anyway, my whole point is that it's not uncommon for galaxies to interact with each other in clusters. Okay. How many galaxies are there? Well, in the mid-90s, with Hubble, and I think this is a link also you can click on to get your own field. What people decided to do was to train the Hubble Space Telescope to look at an otherwise blank patch of sky for about 10 straight days and just shutter open. Right? It's like a really long time on the camera. And the area of the picture is really, really tiny. It's about as small as you can make out with your eye. It's about 1 minute arc across square. Something like if you just take a period at the end of a sentence, book, hold it at arm's length, that's about the size of this picture. The whole image on the left is about 1 minute arc across. Very tiny, teeny, tiny little just kind of. So what happened was, if you just let the light fall and accumulate on the camera, what you get out of it is this image. And I encourage you to go get this image, blow it up on your desktop, and just sort of poke around in the image for it. It's amazing. There are about 10,000 galaxies in this picture, all in that little pinprick of the sky. Blow that up and let the light. Your eyes are really sensitive. You would see about 10,000 galaxies in the image. And you can see all sorts of galaxies in all different phases of evolution and time of the universe, age of the universe. Here are some elliptical galaxies, colored orange and red. Oh, look at this. There's a little spiral. You can tell when you look at these images if there is a star in the foreground. Here's one. Because the Hubble Space Telescope has 4 little pieces of metal that help support the mirror, some of the instruments inside. And so that creates little diffraction spikes. And so when Hubble looks at a star, you get these little 4 spikes around it. So every time you see something like that, you know it's a star in our galaxy in the foreground. But everything else in this image, all the little points of light in this image, are distant galaxies. So Hubble is imaging galaxies very, very deep, way, way, way back. Here's the key point that we're going to hit next week, is the farther away these galaxies are, the longer the light is taken to reach us, light speed. So some of these galaxies, the light's been traveling to us for 10 or 11 billion. So in a real sense, these telescopes are like time machines. We can see. You wonder, what was the universe like 5 billion years ago? No one was there to see it. Well, that's actually really easy, because all we do is we go look at something that's 5 billion light years away. Light's just getting to us. And so then we can see what the universe is like directly 5 billion years ago. So by looking at this and just sort of taking slices of this image closer and closer to us, we can get a sense of how the universe has changed over time. Very, very cool. So if you just scan around this image, you can see lots of really beautiful examples. Nice little spiral. And then little clusters. And these are the subject of current great interest way, way, way in the background. You see these dwarf galaxies that were born very, very soon after the Big Bang. And so intensely studying these to see what the conditions were like in the very early. We'll talk more about them. But this is just an amazing picture. And so this was one deep field image. Over here on the right, you see another one that was done close to the Big Dipper, where you take just a little piece of sky here, and then you blow it up, and then you take a little piece of that, you blow it up. What do you get? 10,000 more galaxies. So everywhere you look, if your eyes were sensitive enough, every little speck of sky that you blow up is just filled with galaxies, each with hundreds of billions of stars, right, all the way back into. So it's just an incredibly vast universe. What we'd like to do to set us up for next week is we'd like to be able to make a map of where these galaxies are distributed in space. What does the universe look like in 3D map galaxies? So in this Hubble Deep Field, what would be cool is if we could assign a distance to every one of these galaxies. So what we're going to use is what's called Hubble's law. Now, before, we didn't really go over this. It's just a little point in the book. It's a pretty easy point. For galaxies that are close to us, what we can do, and the globular clusters that are close to us, we can look at variable stars. Variable stars pulsate. What they're really doing is they're just expanding. So it's almost like sort of a bell ring. It's really good at it. Well, what kind of bells make really deep sound, low pitch, low frequency sound? Big bells, right? Small bells make high frequency. So it's probably not surprising that stars that oscillate slowly tend to be really, really, and stars that oscillate rapidly tend to be smaller. That's the whole idea. So what we do is we go look at some nearby galaxies where we can image individual stars in these galaxies and we watch them. And by watching them pulsate, we get a good idea of what their actual luminosity is. And remember, that's the whole deal, because if we know the luminosity and how bright they look, we can then calculate the distance because it's done something. So for nearby clusters and nearby galaxies, it turns out we can use variables. It's awesome that we can do that. Variable stars are almost like little blinking signposts in the heavens telling us how far away they are, right? It's pretty easy. But once you get far enough away in these galaxies, look at these galaxies, you're not going to be able to see individual pulsating stars in the galaxy. So we can actually do something else. This was a discovery by Slipher and Hubble. What they discovered was that when they looked around at different images of the universe, all galaxies except the ones in our local group, because we're gravitationally, but all the other galaxies in the universe are running away from. In other words, they all have, remember how this works, the Doppler effect. They all have a redshift. Now that's weird, right? Nobody expected that. You would feel weird if you went to a party and you looked around you and everyone at the party is walking away from you in every direction. So we felt kind of odd when we looked around the universe and every galaxy had a redshift, except the ones in our local, right? Stops. So all the other galaxies in the universe are running away from you. They all have a redshift. And then when Hubble investigated this, what he did is he compared the redshift to known distances to these galaxies from these variable stars. And what he noticed was that there was a pattern. It's not just that the galaxies are running away from it, but that there's a pattern. Here's the pattern. The pattern is even more. The farther away the galaxy is from us, the faster it moves. That's even more bizarre, right? It's a really, in fact, it's a pretty tight relation. So galaxies that are close to us are running away slowly. Galaxies that are far away from us are running away fast. And there's no exceptions to that. You're not going to look far away and find a galaxy that's moving very slowly. The galaxies that are close to us, none of them are moving really fast. So it's a good, tight relationship. But it's mysterious. Why would they, not just why are they all running away from us, but why in this particular pattern? We'll come back to that next week. But what this enables us to do, since the relationship is so tight, works for every galaxy, is we can just write it down mathematically, what we say is the speed of the galaxy V is just proportional to its distance, d. The proportionality is just this thing, h. This is called, it's just a number. This is called the Hubble constant. If you remember graphing things back in math class, that's just the slope of the graph. So all it says is the greater that d gets, the greater that v gets. So the greater the distance, the greater the speed. And then h just tells you how much greater it is. So that's called the Hubble constant. It's just a number. Right now, we think this number, this has taken a long time to get, right? A lot of times in science, we just write these things down like, oh, to discover. This was not easy to discover. The Hubble constant was narrowed down over many, many. When I was in school, Hubble constant was supposed to be somewhere between, the number was somewhere between 50 and 100. That's a wide range, right? That's like a factor of 2. Nowadays, we've been able to narrow it down so that we say it's about, for this class, we're going to use the value 70. I'll put the unit, but it's just a number, and now its value is 70, and we know it to about plus or minus, we'll say plus or minus. So it could be as high as 73, as low as 67. But that's the whole process of science, is that you start narrowing that down through lots and lots. Okay, here's how we use it. It's 70 kilometers per second per megaparsec. Okay. Remember, parsec is a typical distance between stars. That's not going to work for galaxies because galaxies are enormous. A typical distance between galaxies is on the order of a megaparsec, like between us and the Andromeda Galaxy is something. Mega meaning million. So for every megaparsec a galaxy is away from us, its speed increases by 70 kilometers per second. Sounds okay. So here's how we use it. First of all, what we're looking for is d, right? So let's do just a tiny bit of algebra. D is going to be over h. We're looking for d. We want to know the distance to the galaxy. H we know. That's just a 7. So how are we going to get, how we're going to get it? It's actually really easy. We're going to get it the Doppler. Remember what that is. The Doppler effect is that change of wavelength because of the movement of an object. So here's an example. Here's the spectra of a galaxy. And here we have what you want to look for. That. That's usually the easiest to see. Galaxies have emission lines. So usually from star-forming regions. And so these are spikes up. And look what's up there. That says H alpha, right? Sandwiched in between two. There's H alpha. So what we do is go and look at what that H alpha value is. What is the wavelength of that H alpha? We can leave it extra. It's going to be. So if I look at that, it looks to me like, if I drew a totally straight line, it looks like the wavelength of H alpha, lambda, is about 7,200 angstrom. Okay, but you might remember when we were doing this before, what is the wavelength of H alpha in a laboratory? The rest wavelength. If something is not moving, if there's no Doppler shift, what should the wavelength of that be? It should be, this is lambda, we'll say observed, lambda tab, should be 65, 61. All right, so that number is greater, right? So it's been redshift towards the red end of the spectrum. Our job is to figure out how much it's been shifted. Really what we want is a percentage. That's what we're going to call the redshift. So how do you get a percentage? This is no different than if you're buying something, it was $6,500, now it's $7,200. What percent did it go up? So we're going to use the same procedure you would just use in everyday life. What you say is By the way, the redshift is usually... So the redshift is just going to be what we observe minus what it is in the lab. Then we just divide by the original. Okay, let's do that. So it's what, 7,200? 32 561 divided by, and it looks like it's 0.097. Okay, so that's the fractional redshift. If you want it as a percent, just multiply by 100. Just move the decimal point over 2 spots. And this is 9.7%. So it's a 9%, almost a 10% redshift. Okay, how does that help us? Because the amount of redshift tells us, the speed at which it's moving. So if it's moving at 9.7, if the redshift is 9.7%, it's moving at 9.7% speed of light. Simply do it. So all we have to do, the speed is just the redshift times the speed of light. And so this is going to be 0.097. The speed of light that we're going to use is 300,000 kilometers per second. Fast light travels. So if I do that, I'm going to get about, it's about 10%. That's going to be about 30,000 kilometers per second. It's my V. Okay, so now I have everything I need. Calculate the distance. The distance is going to be 30,000 kilometers per second divided by Hubble, 70 kilometers per second per megaparsec. Means that unit cancels. If you've done unit conversion history and stuff, those units cancel. Anyway, you just divide the 30,000 by the 70, and here's what you get. 429 megaparsecs. There we go. That's the distance to the galaxy. So again, just so you don't lose the forest for the trees, all we did was we just calculated the redshift by looking at the spectrum. It's pretty easy to do. You just look at that H alpha. So calculate the redshift, and then you can figure out how fast it's moving. You divide by the Hubble constant, boom, you got your distance. So that's how we do it. That's how we can measure the distance to all those galaxies in Hubble Deep Field or any other galaxy we see. We just measure the redshift, which turns out to be really easy, and just do a pretty simple couple-step calculation, and then we know how far away it is. And so then we can start making a map. So what does the universe look like? What are these 3D maps of the way the universe looks? That might be pretty interesting. We're the first generation of human beings to know what the universe actually looks like on really, really large scale. So what does it look like? Cliffhanger. Tell you next week.